Hello students, welcome to lecture 2 of rotational dynamics. The first topic that we are going to discuss today is circular motion. Circular motion and its types. So we know that circular motion is nothing but motion of a particle on a circular path. If we talk about the types, there are two types, that is uniform circular motion and the second is non-uniform circular motion. Today we are going to discuss both these types of circular motion in a little bit detail. So first, let's start with uniform circular motion. So let's start with the definition first. So uniform circular motion is nothing but circular motion with a constant speed. Circular motion with a constant speed v. Now let's say this is our circular path. The speed is always going to be tangential, so we are considering anti-clockwise circular motion. So these are the directions of v's at all the points. Okay, so we are considering a anti-clockwise circular motion. Now in the last lecture we saw that the speed v is nothing but r omega. V is equal to r omega. This is the magnitude equation for the speed. V is constant, r, which is the radius of the circle, is also constant. Therefore omega is also constant. We have also seen a relation that t is equal to 2 pi by omega. And since omega is constant, our time period capital T is also constant. So whenever we have uniform circular motion, the speed of the particle is constant, the angular velocity is constant, and the time period is also constant. Okay. Now, when we say that the speed is constant, v is constant, then the acceleration responsible to change the speed, which is at, we call it tangential acceleration. This tangential acceleration must be equal to 0. So in uniform circular motion, a point to remember is that the tangential acceleration is 0. Now we also saw that omega is constant. Therefore angular acceleration alpha, which is equal to d omega by dt, is equal to 0. So whenever we have uniform circular motion, the tangential acceleration at is equal to 0 and the angular acceleration alpha is also equal to 0. So let's summarize. So for uniform circular motion, your speed is constant, angular velocity omega is constant, time period is constant, tangential acceleration at is equal to 0. At tangential acceleration is nothing but dv by dt. V is constant, therefore at is equal to 0. Alpha is also equal to 0, and alpha is nothing but angular acceleration d omega by dt. Now, as we can see that tangential acceleration and angular acceleration both are coming out to be 0. But there is one non-zero acceleration. And that is nothing but centripetal acceleration. And that centripetal acceleration is non-zero in uniform circular motion. Now let's see what is that centripetal acceleration. So let's say we have this circular path. This is the center. Okay. And let's say this is the radius. Now a particle is on the circumference. Whenever there is a particle on the circumference of the circle moving in a circular path, there is an acceleration acting towards the center. So centripetal acceleration acts along the radius and it is towards the center. So if we talk about the magnitude of centripetal acceleration, AC, it is V square by R, but V is also R omega. So it can be written as R square omega square upon R, which gives us AC is equal to R omega square. Or AC can also be written as V square upon R, and in place of R, we can write V by omega. V and V gets cancelled, omega goes up, and we have V omega. So there are three formulas for centripetal acceleration. The first is V square by R. Then we have R omega square. And then we also have V omega. And the centripetal acceleration is nothing but an acceleration acting of the particle moving in a circular motion. It acts along the radius towards the center. Now, if we multiply mass to this centripetal acceleration, we get a force, and that force is nothing but centripetal force. And centripetal force is obviously in the direction of centripetal acceleration. Therefore, this centripetal force is also radial and it is towards the center. So we can also write down the formulas for this centripetal force. Just multiply mass to centripetal acceleration. So we have mv square by r, or mr omega square, or mv omega. So I'll box up the important formulas of centripetal acceleration and centripetal force. Okay, so this is an acceleration which is non-zero in uniform circular motion case. Otherwise, the tangential acceleration at as well as angular acceleration alpha both are 0. So I'll just summarize this centripetal force and acceleration. Centripetal force radial force towards center, acting on a particle moving on a circular path. Moving on a circular path. Acceleration corresponding to centripetal force is called as centripetal acceleration, and it is radial and towards center. And these are the formulas: centripetal force mv square by r, m r omega square, mv omega, and AC, just remove the mass from centripetal force, v square by r, r omega square, v omega. Okay. Now, the next topic is non-uniform circular motion. Now, when we studied uniform circular motion, we saw that the direction of velocity was changing at every point, but the magnitude of velocity, which we call speed, was constant. Here, in non-uniform circular motion, the first point that we need to remember that direction as well as magnitude of velocity, which we call speed, they both change. They both change. So over here we have centripetal acceleration, that is non-zero. By the way, I just forgot to tell one thing, that this centripetal acceleration is responsible to change direction of velocity. Direction of velocity. Okay, now let's get back. So in non-uniform circular motion, we have non-zero centripetal acceleration as we had in uniform circular motion, but along with non-zero centripetal acceleration, we also have non-zero angular acceleration and non-zero tangential acceleration. Now, why do we have this non-zero tangential acceleration? Let's first address that thing. So over here, v is not constant. The magnitude of velocity, which is speed, is not constant and it is changing. So tangential acceleration, which is dv by dt, is not equal to 0, because when v was constant, its derivative was 0, but now v is not constant, therefore its derivative is non-zero, and therefore we have a non-zero tangential acceleration. Now let's discuss why alpha is not equal to 0. So we saw that v is equal to r omega. This was the magnitude equation. V is variable. The radius value of the circular path does not change, but v is variable, therefore omega also has to be variable. And if omega has to be variable, then omega is not constant, and therefore alpha, which is d omega by dt, is non-zero. So we have a non-zero angular acceleration as well as a non-zero tangential acceleration, along with non-zero centripetal acceleration. Now, since we have non-zero tangential acceleration and non-zero angular acceleration, and they are vectors, so it is very important to decide and point out the directions of tangential acceleration and angular acceleration. So the next topic that we are going to see is directions of angular acceleration and angular acceleration, that is alpha, and tangential acceleration, that is at. Okay, so I have considered two circular paths over here to decide the directions of alpha, angular acceleration, and at, tangential acceleration. So let us see how to find out the directions. Now in the first case, we will consider an anti-clockwise circular motion. An anti-clockwise circular motion, we know that omega is a tangential vector. Omega is an axial vector. Therefore, the direction of omega will be along the axis. And if we are observing from the top, then since it is anti-clockwise, the direction of omega will be towards us, and since we are observing from the top, the direction of omega will be upwards. Now, what I am stating in this case is that omega is constantly increasing. Which means V is also increasing. Now, if the value of omega is continuously increasing, then in that case, the alpha bar vector will be parallel to omega bar. On the other hand, if we have a similar anticlockwise circular motion, omega bar will be upwards. But if omega is decreasing, which means V is also decreasing, then in that case, alpha bar will be anti-parallel to omega bar. So this is the rule that you need to remember, that if the magnitude of angular velocity is increasing, then angular acceleration alpha bar is parallel to omega bar, and if the magnitude of angular velocity omega bar is decreasing, then alpha bar is anti-parallel to omega bar. Okay? So let's summarize the rules for direction of alpha bar. Rules for direction of alpha bar. So the first rule is, if omega is increasing, alpha bar is parallel to omega bar. And second, if omega is decreasing, then alpha bar is anti-parallel to omega bar. The rules are same rules for AT. Bar. So the first rule for AT bar is, if V is increasing, AT bar is parallel to V bar. And second, if V is decreasing, then AT bar is anti-parallel to V bar. Okay? Let's quickly consider a case over here where we will plot the direction of AT bar. So I am having a circular path. This is the center, and the motion is in anti-clockwise direction. So at this point, the velocity will be upward like this. So this is V bar. Now if I state that the magnitude of velocity, that is speed V, is decreasing, then in this case, the AT bar will be anti-parallel to V bar. AT bar will be anti-parallel to V bar. If velocity was increasing instead of decreasing, then AT bar would have been parallel to V bar. Okay, so this is how you plot the directions of alpha bar and AT bar for the cases of increasing speed and decreasing speed. Now, this is not at all important from 12th state board point of view, but I thought it important to share this information that it is not necessary that alpha bar must be parallel or anti-parallel to omega bar. Alpha bar can be at some angle theta to omega bar. But in this case, when alpha bar is at some angle to theta to omega bar, alpha bar will change both direction as well as magnitude of omega bar. And this is a complex case which is not important to us. Whereas in the case when alpha bar is either parallel or anti-parallel to omega bar, it will not change the direction of omega bar, it will just change the magnitude of omega bar. Okay, now let's move on to the last topic of this lecture, which is nothing but the net acceleration during non-uniform circular motion. So now we just saw that in non-uniform circular motion, we have a non-zero value of AC, that is centripetal acceleration, as well as a non-zero value of AT. AT is tangential, centripetal acceleration is radial, therefore they both are perpendicular. Now the net acceleration which we call A is nothing but the vector addition of this centripetal acceleration and tangential acceleration, and since these both accelerations are perpendicular, the net acceleration can be written as under root AC square plus AT square. Why? Because they both are perpendicular. So this is the final formula that I wanted to add to this lecture. That is the formula for net acceleration or total acceleration during non-uniform circular motion. And that is nothing but the formula of net acceleration, which is under root AC square plus AT square. So in the next lecture, we will start with the derivations of angle of banking, maximum speed limits, etc. Till then, keep studying. Thank you.